In the last three videos, we focused on discrete distributions, that is, probability distributions where the random variable of interest was discrete in nature, meaning it could only occupy finite or limited values. For example, when we looked at people or objects within a bag or box or shirts, all of these could only assume integer or whole number quantities. You can't have half a person. You can't pull out half an M&M. You can't stack a quarter of a shirt, etc. Now we'd like to shift gears and look at continuous variables. For example, suppose I have an experiment where I measure the height of an individual. And let's suppose that x is going to be the height of the person in meters. My first person could be 1.7 meters. My second person could be 1.79 meters. My third person could be 1.799 meters. My fourth person can be 1.7999 meters. And I can keep going on forever. Every single time I can add a decimal place and add another number. And I could go on for an infinite amount. So with continuous variables, my data set is infinitely large. Now you can argue that a discrete variable can also have an infinitely large data set. You can count all the way through the integers to infinity, but in this case, between any two numbers, between any two outcomes, there is still an infinite amount of possibilities. Between 1.799 and 1.7999, I can have 1.7991, 1.79911, and so on and so forth. So it's not even countable. You can't start or end anywhere. In that sense, continuous variables also form a continuous spectrum or a continuum, hence there are no gaps. What this means for our probability distribution is that we get a smooth curve. And the way you can interpret this is that our domain for our function, so our probability distribution, is the same thing really as a function of x, our random variable, and our domain in this case is x such that x is an element of the real numbers. And you can have a certain range in here of values, or an interval rather. But more importantly, in this case, x can be any possible decimal value. So just like with discrete distributions, continuous distributions come in a variety of forms and types, but for the purpose of this course, we're going to be focusing on the normal distribution. Now it's called the normal distribution because it's seen in many places and has many applications. Whether you're in a lab for chemistry or physics, or you're simply observing nature or wildlife, you're eventually going to come across a normal distribution, so it's pretty normal to find one, hence the name. Now if we were to draw a normal distribution, we can start with our axes, and once again, it's a continuous distribution, so we're going to get a smooth curve as our function. So on the bottom over here, we have our random variable x, and then on our y-axis, we have the associated probability. The distribution can range from negative infinity all the way to positive infinity. And it has its largest value at the mean. So for the purpose of the distribution we're drawing, we're going to assume our mean is equal to 0, and our standard deviation for this distribution is going to equal 1. So our largest value is going to be at our mean of 0. It's right over here. And then we're going to slowly dip off in the shape of a mound or a bell as we get farther away. So this is going to be your normal distribution. Now notice that as we get to larger values, the probability decreases. So in reality, once you reach very high values, depending on what data set you're observing, but certainly as you get to infinity, your probability becomes very small, and so it's very, very, very unlikely that you observe high outcomes for your random variable. Now, to summarize the characteristics of the distribution, it's centered at its mean, so it's centered at mu, and it's symmetric about mu, so each side is a mirror of the other. Its spread and its height, so its spread and height are a function of its standard deviation. And so if I had another distribution with a mean of 5, let's say, and a standard deviation of 100, we could approximate it. We'll draw this a bit on the side since we're going to center it at 5 this time. So if this is 5, we have a standard deviation of 100, so our data is really spread out. So we're going to have a smaller height, and it's going to be more spread and centered at 5. Finally, the area under the curve, so this region in yellow, area under the curve, since it's a probability distribution, the area under the curve represents the entire probability set for all the outcomes. Area under entire curve is equal to the probability of the entire sample. So that's the same thing as saying the probability of the sample set, which is equal to 1. So the probability under the normal distribution is equal, or the area under the normal distribution is equal to 1 in all cases. That's why when we increase the standard deviation or the spread of the data points, we need to decrease the height of the distribution. So now on to some properties of continuous distributions in general, but all of these also do apply to the normal distribution. So let's just draw a distribution quickly so we can refer to it as we list these probabilities. So number 1, we mentioned this earlier, the probability that x is within a range of values or an interval of values is equal to the area under the curve for this range. So let's say I was interested in the probability that x is between 4 and 6. So the probability that x is greater than or equal to 4, but less than or equal to 6. That's going to equal the area under the curve for the interval 4 to 6. So let's say this is 4 and this was 6. The probability that x ends up between 4 and 6 is equal to that area. Now from this, the probability of any single point or any single outcome is equal to 0. So the probability of x equaling 4 is equal to 0. Now you can look at this in two ways. If we use the area analogy, if we look at x equaling 4, we're only going to have a line. A line is in one dimension, and so its area is equal to 0. It has no width. The other way you can look at it is the probability that x is equal to 4 is equal to the number of successes or successful outcomes divided by the total number of outcomes. Now we just saw that a continuous distribution can assume infinitely many possible values. So the total number of outcomes is infinity. The number of successes is only x equaling 4, so it's only one possible success. So we have the probability of x equaling 4 is equal to one outcome out of infinitely many outcomes, which is equal to essentially 0. Instead, the value at P4, so P of 4, the value or the height at this point gives the probability that x is near 4. So the value of the distribution at x is equal to 4 gives us the probability that x is near 4. So perhaps from 3.5 to 4.5. Finally, since it's a discrete, or rather since it's a continuous distribution, there's no real beginning or end between any two values. And so in a discrete distribution, when we had the probability that x is less than 6, we could say that that was equal to the probability that x is equal to 5, since that's the next number below 6, or less than 5. So in a discrete distribution, the probability that x is less than 6 is the same as the probability that x is less than or equal to 5. In a continuous distribution, the probability that x is less than 6 is simply equal to the probability that x is less than or equal to 6, since we just saw that adding that or equal to 6 is simply adding 0, and there's no real beginning or end from less than 6 and less than or equal to 6. You can't draw that line. And so the probability that x is less than 6 is the same as the probability that x is less than or equal to 6. And a final point, if we look at our distribution one more time, we saw earlier that the entire area below the distribution is equal to 1. Now a neat trick that we can use from this information is that suppose this is our point 6. If we want to find the probability that x is less than or equal to 6, so we want to find the area over here, we know that the entire area is equal to 1. So we know that all of the area is equal to 1. So the probability in red is 1 minus our region over here in blue. And our region in blue is the probability that x is greater than 6. And that's the same thing as saying greater than or equal to 6. So the probability that x is less than or equal to 6 is equal to 1 minus the probability that x is greater than or equal to 6. Likewise, the probability that x is greater than or equal to 6 is equal to 1 minus the probability that x is less than or equal to 6. And if we add the probability that x is less than 6 and x is greater than 6, then we'll simply get 1. So I'm sure you've been wondering, how do we find the areas under the normal distribution? And I can tell you right now, it's not something trivial, and it's certainly not easy to do. So the way we actually go about these problems involves something called the z-score. So mathematicians have calculated the areas under the standard normal distribution. And the standard normal distribution is the one where the mean is 0 and the variance and standard deviation are equal to 1. So if we have two distributions, the one on the left is going to be our standard distribution. So it's going to be centered at 0 since that's its mean. And it's not going to be too compressed nor too spread out since it has a standard deviation of 1. And then on the right we can have any possible normal distribution. So it can have any spread and any mean. On the left side, our standard distribution we can find the area under the curve because it's somewhere in a table. And I'll show you how to use that table in a couple of minutes. For our distribution on the right, so any normal distribution that has some mean and some standard deviation, finding the area between any 2 points is going to be difficult. So what we do is we calculate the z-score. So the z-score is a score for any point that tells you how far or how many standard deviations a point is away from the mean. So if I have a z-score, suppose z for some point was equal to 1, then that point, so let's say z1 corresponding to x1, if z1 was equal to 1, then x1 is 1 standard deviation above the mean. And it's above because z1, 1 is positive, so if it's positive, that means the point was above the mean. Let's say z2 for a point 2 was equal to negative 2. That means that x2 is 2 standard deviations below the mean. And so the formula for the z-score, z of any point, so let's say z of I, is equal to that point, xi. So I is just a number for which point you're looking at. So if we're looking at the 5th point, then z5 is equal to x5 minus the mean of the data set. So that'll give you the distance between the point and the mean. If the point is above or greater than the mean, you're going to get a positive value. If it's less than or smaller than the mean, then you're going to get a negative value. We then divide by the standard deviation to find how many standard deviations away the point lies. So that's our formula for the z-score. Now it turns out that if we take every single x value that we have in our any normal distribution up here, if we take every single x value, so on the right we have a function, or we have a probability distribution of x, and so we have a function of x. Our variable of interest is x. If we replace all of those x's, so instead we use the z-score, so we get a function of z instead. So essentially, anytime we see x, we're going to replace it with x minus the mean divided by the standard deviation. What we get is we transform that function into the standard distribution. And a bit of intuition as to why is if we simply look at the point that is at the center over here from the mean, the z-score for that point is going to be the mean. Since that's the point we're looking at, it's equal to the mean. So the mean minus the mean divided by sigma, mean minus mean, is going to equal 0. So we're going to take it right away, we're going to center it at 0, and everything simply works out. You're going to get a standard deviation of 1, and you're going to get the standard distribution. So to solve these problems with normal distributions and z-scores, you're going to want to transform from x to z, then solve. And as a quick example, we're not actually going to solve it, but just to give you some insight as to what we're doing, let's say we wanted to find the probability for some distribution that x is less than 4. And let's say that this distribution had a mean of 2 and it had a standard deviation of 2. Finding the probability that x is less than 4, I don't know how to do that, since we're not dealing with the standard distribution. So what I'll do is I'll find the probability that z and my x that I'm interested in is x is equal to 4. I'm going to transfer that to the standard distribution. So I'm going to take 4, I'm going to subtract the mean of the distribution, which is 2. Then I'll divide by 2. So the point x equals 4, if I take that and go to the z world, I'll get 4 minus 2 divided by 2, probability that z is less than 1. So over here, let's say this was the point 4, and it corresponds to that entire area. In the next distribution, and just to keep things consistent, let's say this was actually equal to 4. So let's say that was equal to 4. Then in my standard distribution, that value of 4 would correspond to a z value of 1, corresponding to that area. And so the probability that x is less than 4 has the same area on both curves, and I can find that area when I use the standard distribution. So here's the z-score table, and the way we use this table is that if we have a distribution, a standard distribution, and we have a some z value, if we find this z value correctly on the table, we'll be able to get the area under the curve below this z value. So from a negative infinity all the way up to this z value. So suppose we want the probability that z is less than or equal to 1.22. What we do is we look for the first two digits, so the one in the ones place and then the one directly after the decimal. So we're looking for 1.2. We're going to do that in this first vertical column. So we're going to look for 1.2. We'll find it right over here. Then, so I'll put that in blue. Then what we'll do is we'll look for the third digit in the horizontal row at the top. So in this case, we're looking for 2. So not 0.0, not 0.01, but 0.02. And you can notice that 1.2 plus 0.02 does indeed equal 1.22. And then we'll find where these two intersect, so the column and the row, where they intersect at 0.8888. So the probability that z is less than or equal to 1.22 is equal to 0.8888. In other words, the area under the curve below the value of 1.22 for a standard distribution is equal to 0.8888. Now if we want the probability of z being greater than a certain value, so let's use 1.22 once again, all we have to do, since now we're interested in this area in green, we know that the entire distribution has an area equal to 1. So the area in green is 1 minus the area in red, which is what we just found. So 1 minus the probability that z is less than or equal to 1.22, which is equal to 1 minus 0.8888, or 0.1112. And if we want to find the probability that x, or z rather, is between two values, so what's the area under the curve between 1 and 2, so this area over here, all we have to do is we find the total area below 1, so the area in blue. Then we find the total area below the lower value, so 1. And we take the area below the greater value, subtract the area of the smaller value, and we're left with what's in between. So the probability that z is greater than 1 but less than or equal to 2 is equal to the probability that z is less than or equal to 2 minus the probability that z is less than or equal to 1, which, if you use the table, is equal to 0.9772 minus 0.8413, or 0.1359. So the area under the curve between 1 and 2 for the standard distribution is equal to 0.1359. And just as a note, this is the positive side of the table, positive z-score table, so all the values in here are going to be positive. But there's another sheet that will have all the negative values. So it's going to have a negative 0.1, negative 0.2, negative 0.3, all the way to negative 3.4. And it can be used in the exact same way. So now for an example, we have an experiment involving the heights for many giraffes. And this experiment, the data that we collect, it can be modeled by a normal distribution. So they found that the average height was 6 feet, and the standard deviation for this height was 14 feet. And we want to know what the probability is of selecting a giraffe that is shorter than 6 feet. So this is part A. Part B asks what is the probability of finding a giraffe that is greater than 7 feet tall. Part B. And then we want to know what is the chance that our selection is between 4 feet and 8 feet. So part C. So we're going to let x be the height of the giraffe in feet. And then we have that x can be approximated by the normal distribution with a mean of 6 feet and a standard deviation of 14. And so for part A, we're trying to find the probability that x is less than 6. So what is the probability of selecting a giraffe that is shorter than 6 feet? Well, that's equal to the probability that x is less than or equal to 6. And if we transfer it to z-scores, it's the probability that z is less than or equal to 6 minus, our mean in this case is also 6, divided by 14, which means it's the probability that z is less than or equal to 0. Now, you don't even need to use the z-score table in this case, since it's a symmetric distribution, and we know that the standard distribution is centered at 0, and so just by intuition, we're going to have the left-hand side of the distribution, which is exactly half of the distribution, so the probability is going to equal 0.5. If you do decide to use a table, you will get the same answer. So the probability of selecting a giraffe that is shorter than 6 feet is about 1/2. For part B, what is the probability of selecting a giraffe that is greater than 7 feet tall? So what is P of x is greater than 7? Once again, that's equal to the probability that x is greater than or equal to 7. If we transfer to z, we have z being greater than or equal to 7 minus 6 divided by 14. And then recall that our table gives us values that are below our z value, not above. So we have to change this to 1 minus the probability that z is less than or equal to the number over here, the fraction. If we make it a decimal, we'll get 0.0714, and that's approximately equal to 0.07. So that's what we'll use. It's close enough. And that's equal to approximately, since now we're not dealing with the exact value, we just rounded our answer. So it's equal to approximately 1 minus 0.5279, which is equal to approximately 0.4721. So the probability that you select a giraffe in this data set that is greater than 7 feet is around 47%. Now finally, what is the chance that our selection is between 4 feet and 8 feet? So for part C, what is the probability that x is greater than or equal to 4 or less than or equal to 8? Well, we just saw earlier that it's equal to the larger value, so the entire area below our larger value, minus the entire area below our smaller value, and what we're left with is what is between them, which is exactly what we're looking for. If we transfer to z, we'll get the probability that z is less than or equal to 8 minus 6 divided by 14. So our value minus the mean divided by the standard deviation, minus the probability that z is less than or equal to 4 minus 6 divided by 14. That's equal to the probability that z is less than or equal to 0.143 minus the probability that z is less than or equal to negative 0.143. Once again, we're going to round both of these numbers since 0.143 is close enough to 0.14. If you wanted to, you could take the two values, so we could find the probability z less than or equal to 0.143. It's somewhat halfway between 0.14 and 0.15. It's closer to 0.14, but it's also somewhat halfway. So what you could do is you could find the area associated with below 0.14. You could find the area below 0.15 and then average them. So that's a possible option, but in most cases you should be allowed to simply round to the closer value and use that. So if we use 0.14, we'll get the probability that z is less than or equal to 0.14 being 0.5557 minus the probability that z is less than or equal to negative 0.14. So that's on the negative side. It's going to be less. It's going to be 0.4443. And if we plug that into our calculator, we'll get that the area in between is 0.1114. So the probability that we select a giraffe that is between 4 feet and 8 feet is equal to 0.1114. And that's how you use the normal distribution with your z-scores.